Welcome to part 3. Okay, I left off talking about 3 uncertain input parameter values. So the number of tasks completed on a particular weekday, the number completed on a typical weekend day or weekend, and then the quality of the work. Were the tasks completed well, high quality? Yes. If yes, then 1. If no, then 2. We need to start saying something about now how likely values across this range are. And so this is where we start getting into characterizing the distribution. Crystal Ball can help us with this. So once you open up Crystal Ball, there's a tab called Distribution Gallery, and this is a really handy thing. It shows you a little pop-up like this, and you'll see a bunch of probability distributions here that can be used to describe or characterize uncertainty in input parameter values. In Crystal Ball, you can click on these different distributions and learn more about them. There are other ways to learn about these distributions. You could read about it in the textbook. We will talk about different distributions over time in the class. We've already talked about distributions like exponential and Poisson for queuing. Remember that the exponential distribution is often used to characterize or to describe inter-arrival times to a system or service times within a system. And the Poisson distribution is used to characterize or describe the number of people that arrive within a certain time frame. Okay, I'm sure you all have met different variables that we believe are distributed normally, characterized by the normal distribution with a certain mean and standard deviation. Over time, you're going to meet more and more of these probability distributions, and I'll try to help you understand the types of input parameters that tend to be characterized using different distributions, and this sort of intuition around what these distributions mean in terms of likely values for input parameters that are not known for sure. So again, these are screenshots taken from Crystal Ball's distribution gallery, which I really like. So here's a screenshot looking at the discrete uniform distribution. And if you were to type in a minimum value and a maximum value, here I have 1 and 6, you see that this distribution, what it says, if you were to use this to characterize uncertainty around an input parameter, is that any value between 1 and 6, there's a finite number of values, right? Only 1, 2, 3, 4, 5, or 6 are possible. And every one of those values is equally likely. So if I were to take 100%, something's got to happen, and divide that by the 6 values that are possible, each one of those is a little over 15% likely. This helps us, and that's on the y-axis here. So just this little screen here, the screenshot in the distribution gallery, helps us understand what the discrete uniform distribution looks like. And you could play around with the minimum and maximum, and it'll adjust. The picture will adjust. But again, discrete uniform is a good distribution to use if you have an input parameter that is not known for sure. There's uncertainty in it, risk in it, and you know that it's between 2 values, some minimum and maximum, but you think that, and you know that it's only going to take on an integer, a discrete value, and every one of those values within the range is equally likely. Discrete uniform is a great distribution to use. You don't think that the median, the mean, the value in the middle is any more likely than the values on the ends. They're all equally likely. Then this is a good distribution to use to characterize uncertainty around that input value. Here's a very similar distribution. Instead of being discrete, this is the uniform distribution. Again, I've set up a minimum and a maximum of 1 and 6, and what this is saying is that any value between 1 and 6 is equally likely. There's not a finite, there's an infinite set of values that could be drawn from this distribution, and this one should be used if what you know about an input parameter is that you don't know it for sure, but you know that it's going to be something between 2 values, a min and a max. It can take on non-integer values, and anything between that min and the max is equally likely. Here's just some information about the uniform distribution. I want to issue a warning. I just showed you 2 distributions that have very similar names, the discrete uniform and the uniform. They're not the same. The discrete uniform has a finite set of values that can be taken on between the min and the max, only the integer values, whereas the uniform is a continuous random variable. Another example is the normal distribution. So again, for this one, you should be quite familiar with the normal, the bell-shaped curve, which is very common for a lot of variables. For this one, the normal distribution would be an appropriate one to use to characterize an input parameter if what you believe is that the mean is most likely, and that you know something about the variation, and that you know that values that move further and further away from the mean are less and less likely. And this distribution has long tails. So in this case, unless you really do something to truncate the normal distribution, which is not typically done, values for this input parameter that is characterized with the normal distribution can take on, with low probability, really low and really high values, and that needs to be okay if you were using this to characterize uncertainty around a certain input parameter. In contrast, and to start to get away from this problem with the tails that go off into really high and low values with low probability, is the triangular distribution. So this distribution assumes that your value is going to fall between some minimum and maximum, just like with the uniform. But instead of saying that any value between the min and the max is equally likely, here you're saying that you've got a most likely parameter as well. You've got a third parameter that tells you what value between the min and the max is most likely. And then as you see, the probability of values that are further away from that most likely value are less likely to happen. Lower probability. They're possible within this range from the min to the max, but they're lower probability as you get closer and closer to the endpoints. Note that the triangular distribution, it's a really commonly used one. It's very simple. When what you know about an input parameter is you know what its most likely value is, a most likely value, and then you know something about the minimum and the maximum value that the input variable is likely to have. And that's pretty much all you know. You don't know enough to make any assumptions about the distribution between the most likely and the min and the most likely and the max. This is a really simple distribution to use to characterize uncertainty around an input parameter when you don't think the uniform is a good way to go, because the values closer to the most likely are really truly more likely, but you don't know much more than a most likely, a min, and a max. This one, by the way, is truncated. So there is zero probability that this input parameter characterized with the triangular distribution would take on values below the min or above the max. Beta distribution is another example, one of many in the distribution gallery. Now the parameters for this one, there's 4 of them, a minimum, a maximum, so it's truncated. It's continuous, right? Notice that this is a curve, it's not discrete. And you need an alpha and a beta. And the range for the beta is from 0 up to some positive value, and the shape of the distribution depends on the alpha and the beta. It represents variability over a fixed range. Again, not infinite, it's truncated as opposed to the normal. And it's usually used for characterizing the uncertainty around a probability. And we'll talk more about that. But if one of your input parameters is a probability of having a carry given that you've had one varnish or 2 varnishes, for reasons that are sort of outside the scope of this class, the beta distribution, theoretically, is thought to be a really good one to use when you're trying to characterize or describe uncertainty around a probability. Just the way that the exponential was a really good distribution to use to characterize uncertainty around inter-arrival times. And another one that I'll introduce you to here is a custom distribution. So Crystalbal can help you create your own. You don't have to rely on just the distributions that are built into Crystalbal. You can make your own. So in this case, what I'm doing is I'm saying, okay, this is a discrete distribution. Down in the lower left, I'm putting in the values that my variable might take on, 10, 11, 12, and the probability of each one. So basically, you have to specify for Crystalbal in a custom distribution the values that the input parameter might take on and the probability of each. And then what will happen is Crystalbal will draw from that custom probability distribution. And this can be a really good one to use when you have data that tells you that the other distributions aren't really good, but you want to make your own and you want it to be based on that data that you have. It's a good time to pause here and say there's a really neat trick that you can do within Crystal Ball. Crystal Ball has a feature called Best Fit. And so if you have a bunch of data that you want to use to try to characterize uncertainty in an input parameter value, say you've got data on 100 observations of demand for a service over time in the past, and you want to use that to try to characterize uncertainty in demand moving forward. You could use that data, put all that data into Excel, the 100 different values of demand per week over the past 100 weeks. You could use Best Fit. Highlight the data, you click Best Fit. I'll show you how to do this later in class. And what will happen is Crystal Ball will actually tell you which distribution, probability distribution, is the best fit to that data, best characterizes uncertainty, variation in demand, based on the data that you're feeding it. It will fit that data to all the different distributions and tell you which one's best, which is the best distribution for you to use moving forward to characterize that input parameter that's uncertain in your model. So with that, I'm going to stop, and we'll start talking about this gardening example using Excel and Crystal Ball.